Okay guys, in this video we are going to be taking a look at primarily a lot of the time financial type of situations because let's face it, when you put your money say into an investment or a savings account over time, so if I said that this is time and then the amount of money you have, a lot of the time we look at your investments as getting some sort of return as a percentage. And so let's put it this way. If I said at time equals 0, I had $2, maybe 0, comma 2. But every day what happens is my amount of money doubles. So they give me a 200% rate. That means that on the first day here after I started, this is now going to be at a height of 4. 0, comma 4. And if I were to say double that on the next day, it would be at 0, comma 8. And the next day would be at 0, comma 16. You see that when you are earning a percentage of your original amount in order to tell you your amount on the subsequent day, we're looking at exponential growth or decay type of situations. And so we are going to look at a couple of different very important formulas when it comes to exponential growth and decay, especially with finance, but these are these two formulas that you see here. And so we're going to start by just kind of picking apart what these values are. Excuse me. So it says, often we are interested in calculating the amount of interest that compounds on money accounts over an amount of time t. So the following formulas are used to do this. Our first one is for n compoundings a year, and our second one here is, you're going to want to highlight this word, is for things that compound continuously. So we are going to start with this first model, but with both these models, let's go ahead and kind of indicate a few things here. We say that P is our principal amount or our initial amount. And so I'm going to say that this is what we refer to in finance terms as the principal, which is what you started with here. But that just means that it's our amount, initial amount at time 0. So if you let time equal 0, I'll even show you this here. We plug this in for time here. If time is 0, then n times 0 would be 0. And we would be raising all of this to the 0 power, which anything to the 0 is 1. And we would get 1 times our principal, which means that at time 0, our amount is always equal to this first number here. So P is our principal amount. We're going to say R, which is another really important one here, is our rate. Now, this is usually given as a percentage, but it must be written as a decimal. And so the rule is this. Remember that if you are given a percentage, like 50%, and it's decimals here, then to write this as a decimal, we scooch the decimal back twice. That would be 0.5 or 0.50. Hey, likewise, if I had a 7.35% rate, this would be the same thing as a decimal as 0.0735. Okay, so we have to rewrite that as a decimal. In terms of t, we're going to say that this is time. Now, I'm going to say that with financial problems, we tend to say that this is in years. And so we're going to say that here it is in years. And then we're going to fill in n. N is the number of times per year it compounds. Okay. So for instance, up here I said that every day my money doubles. Well, then that would be an n value of 365, because in 1 year it's going to compound 365 times. Now the only other thing that I want to make sure we add up here is A, and that's this left portion. A is the amount at time t. So another way that you tend to see these functions written is the amount at time t as a function of time is given as P times 1 plus R over n to the nt, where this just represents my function value at a given time t. But the neat thing here is I can tell you how much of this principal amount you would have at a given time if you told me some things like, what did you start with? What kind of rate do you have? How long are you going to do this for? And how many times a year should I expect this to compound? So since we are focusing on this first model, and I say that it's for n compoundings a year, you would know that you need to use this first model if anywhere in the problem they say things like your money compounds annually, quarterly, monthly, semi-annually, bi-monthly, weekly, biannually, because they're telling you that it compounds a concrete number of times per year. So very quickly here, let's go ahead and look at these n values. If it's annually and n represents the number of times per year it compounds, then naturally we would say the n value would be 1, once a year. But quarterly, 4 times a year, monthly, 12 times a year, semi-annually means every half year, every 6 months. So in a year that would be 2 times. Bi-monthly would be every 2 months, so 6 times a year. Weekly would be 52 times a year. This is the one you want to be careful about. Biannually means once every 2 years. So if n represents the number of times per year it compounds, then in a given year it would only compound half of a time if it compounds once every 2 years. So keep these in our back pocket, but what I want to do is just kind of look at, hey, could we figure out how much of my initial amount here is left given certain conditions on an investment? So it says on the day of a child's birth, a deposit of $25,000 is made in a trust fund that pays 8.25% interest. Determine the balance on this account on the child's 26th birthday if the interest is compounded quarterly, monthly, and then we're going to finish off with continuously. So with respect to quarterly, let's go ahead and write down a few things here. First one is just this. We started with $25,000 in principal. Other things that I was told was that our rate is 8.25%, which as a decimal would be 0.0825. In this case, our time would be t equals 26. Since this is going to happen on the child's 26th birthday, is 26 years down the road. The only other thing then we need is just to use this formula here, our n value. And so you're going to see that that's really the crux of the matter here. When we have quarterly, we're going to say n is 4. Monthly, we're going to say n is 12. And then here, I'm going to say that n approaches infinity, and we'll get into that in just a moment. So for this first one, quarterly, we're going to say, well, then the amount that I would have at the 26th year would be equal to the initial $25,000 I had times 1 plus our rate, 0.0825, all over n, which in this case is 4 times a year, to the nt, where it's 4 times a year for 26 years. So a lot of people hate doing this just because it's a whole lot of substance, but what I can tell you is if you're careful how you craft it, then you can put this all in at once. So $25,000, that's one too many zeros, times 1 plus, the thing is I can just go ahead and write this fraction without parentheses around it, because inside these parentheses it's going to do this division first before it takes it and adds it to the 1. So we can write 0.0825 divided by 4, end parenthesis, and we're going to raise all this to the power of. Now, because it's 4 times 26 in my exponent, I'm going to wrap my exponent up in parentheses and say it's to the power of 4 times 26. But what I find out is, you know, I suppose that if I've got everything typed in here correctly, 26 years down the road, this child is going to have about $208,000, $208,941. So I'm going to write this here, about $208,941, and since we're talking about money, we'll round it off to 2 places, about 65 cents here. So how would this have been different if it compounded monthly? And so that's the scenario we're going to put right underneath this, and you're going to see that a lot of these things are staying the same. We still have the same principal amount, we still have the same rate, 0.825 here, but it's just going to happen 12 times a year, and so in our exponent we have 12 times a year for 26 years. This time, would you expect your money to be more or less? And so if I compound every month instead of, you know, every 4 months, do you think your money would grow faster? So I'm going to hit second enter, and I'm actually going to go back up here, and we're going to, where my 4 is here, I'm going to delete out my 4. I'm going to hit second delete, which inserts it. I'm going to change my 4 to a 12. I'm also going to delete out this 4. I don't have to delete it, but I'm going to ask it to. Second insert, and we're going to put in a 12 there in its place. And so in this case, we get about $211,989, $211,989, and that is 0.34-ish. So 0.34-ish. And so what I want you to notice is the more times your money compounds, hey, the more money you're going to make. And so my favorite model is this last model where it says it's going to do this continuously. This literally means that it's going to do it every moment of every day, all the time. And so when it is a continuous model, whenever you see this word continuous, we are going to use a different type of model. We're going to use our continuously compounding interest model. So you notice here that we still need some similar things here. We would say that the amount on this child's 26th birthday would be equal to the principal amount, but this time we get to use our natural base e, and this is to the power of 0.0825 times 26. And so the reason why I like this model so much, other than we use natural models, natural-based models to model things all the time, is that it's a lot more concise. So 25,000 e to the power of 0.0825 times 26, and we get 213,551. So about $213,551 and 3 cents. So in terms of these models here, We want to know them both, and we want to know that we use the top one in instances where it compounds only a certain number of times per year, and the bottom one when it's always compounding. But with respect to would I want my money to compound continuously or just like very few times a year, if you're trying to gain money, we want this to compound as continuously as possible because that's going to give you the best possible return on your investment there. So, going forward, we're going to look a little bit more at our natural model there.